Welcome to Calc Chats 26. Today we're going to be diving deeper into improper integrals and talking about where there are discontinuities within the bounds as well as the comparison test. This is a really good example of where we have a discontinuity inside our bounds of integration. So this problem is y equals 1 over the square root of x. We can see that the graph starts up really high and it's steadily decreasing, and we're asked to find the area under the curve from 0 to 1. However, if we plug in 0 for x, we get 1 over 0, which is undefined, which is an issue. So we have to kind of use the idea of improper integrals to split this up so that we can actually solve for this area. So let's take the integral, let's say from a to 1 dx over root x. So from any point a that's less than 1, so it could be 0.5, but the point is our a is kind of over here, and we're going to try to find that limit as a approaches 0 from the positive side. So when we integrate this, we get 2 times the square root of x from a to 1. Because we can rewrite this as x to the negative 1/2. Add 1, divide by that coefficient. So using the fundamental theorem of calculus, we get 2 times the square root of 1 minus 2 times the square root of a. So this just becomes 2 minus the square root of a. So now we can take the limit. So the limit as a approaches 0 from a positive side. So we're going from 1 and we're going to the left. So we're approaching it from the positive side of 2 minus 2 root a. When we approach 0, this eventually just turns into 0. So what we're left with is 2. And so we can say that the limit, or sorry, the integral from 0 to 1 of dx over root x is 2. Improper integrals with infinite discontinuities. These are integrals that become infinite or discontinuous at a point within the integral of integration. So they have some kind of discontinuity, like an asymptote, that would make them infinite if we tried to integrate them regularly. So if we have a few rules, just like we did before. If f of x is continuous on a to b, with a, we see that b is included in the interval, but a is not. So we're assuming that the discontinuity is at the a part of the integral. And we take the limit as c approaches a from the positive side, f of x dx, so just like we did in the last example. The second rule, we take if it's continuous on a to b, so we're assuming that the discontinuity occurs around b, then we take the limit as c approaches b from the negative side. So if my discontinuity was at 4, I could take the integral from 1 to 4, but I would approach 4 from the negative side, from the right side. And then the last one, very similar to the ones before, where we have to split it up. And so our discontinuity occurs at c, so I have to split it up into a to c, and then c to b. And then again, I have to use these limits because my discontinuities occur at c. So we have to split it up, and then we have to include our limits in that one, just kind of like when we had positive and negative infinity, I had to split it up. Our first example, well, technically our second example is 1 over x minus 1 to the 2/3. We notice that that has a discontinuity at x equals 1, and it just so turns out that that discontinuity is in our interval. So first thing we need to do is we need to split this integral up. So split it up from 0 to 1, and then from 1 to 3. and then we can integrate each one separately before we add in the limits. So the integral from 0 to 1, we can say is this is the limit as c approaches 1 from the negative side of this integral 0 to 1. And this integral is the limit as c approaches 1 from the negative side. This is the same as x minus 1 to the negative 2/3. So we add 1, so we get x minus 1 to the 1/3, and then we divide by 1/3, which is the same as multiplying by 3, and then we take from 0 to c. So that's our first step. And then this second integral becomes the limit as c approaches 1 from the positive side, dx x minus 1 to the 2/3. When we integrate this, we get the limit as c approaches 1 from the positive side. This is the same integrand 3, or it's the same integration, sorry, from 0, not 0, from c to 3. And this is not looking very clear, I just noticed. This is a c. So now we have these two limits, and now we're going to use the fundamental theorem of calculus first to evaluate them at the bounds. So we're going to take 3 times c minus 1 to the 1/3 minus 3 times 1 minus 1, or sorry, 0 minus 1 to the 1/3. And then plus the limit as c approaches 1 from the positive side, 3 times 3 minus 1 to the 1/3 minus 3 times c minus 1 to the 1/3. And I realize that I have made a mistake. This lower bound should be 0. Never mind, I realized I had not made the mistake that I thought I did. So we are good to go. So then we can simplify this. So the limit as c approaches 1 from the negative side, this becomes 3 times c minus 1 to the 1/3 plus. This ends up being negative 1 to the 1/3, which is just negative 1. Negative 1 times 3 is positive 3. And this turns into the limit as c approaches 1 from the positive side, and this becomes 3 times 2 to the 1/3. We can write this, rewrite this as 3 times the cube root of 2, and then minus c, 3 times c minus 1 to the 1/3. And so when I take these limits, either way, on either side of 1, whenever I take the limit as c approaches 1, this is going to turn to 0. Because if I think about the cube root function, it kind of looks like this squiggle thing. So from either side, I'm approaching 0. So this goes to 0. And this goes to 0 as well. So what I'm left with is 3 plus 3 times the cube root of 2, and that is my area underneath the curve. Sometimes we are given really hard integrals that we cannot anti-differentiate. So what we use is just a comparison test. So this, again, is really, really similar to our series. And so if f and g are continuous functions, and I have, and this is important to note, that f of g, or f of x, is less than g of x. As long as f of x is less than g of x, if I can find a g of x that converges and is greater, then f of x converges. If I find an f of x that is greater, or sorry, if I can find a f of x that is less than g of x, and it diverges, then g of x diverges. And so again, this is really important that we need to find, if we want to find a convergent series, the greater series needs to be the convergent series. If we think it's divergent, we need to find a series less than. So this is really similar to series, like I mentioned before. When we were proving with series, we found a series that converged and was greater than the original, and then we found a series that diverged and was less than the original. So this is just kind of a recap from series and kind of going into more of what we're covering next kind of unit with series. So here we're given a great example, the integral of cosine squared x over x squared from 2 to infinity. So the first thing that tips us off is this is an infinite bound, so obviously it has to be an improper integral. Next thing I'm looking at is cosine squared x, x squared. I could do this by parts. It might get very, very messy. I don't know if it would entirely work. And all it's asking me to do is if it converges or diverges. So I think to myself, well, I don't really need to find an actual number. I just need to figure out if it converges or diverges. So I'm just going to use a comparison test. And the big thing is what to compare it to. So if I look at the top, cosine squared of x, I know that cosine of x has to be between 0 and 1. And so cosine squared of x obviously has to be between 0 squared and 1 squared. And in this case, it's still 0 and 1. So cosine squared of x has to be between 0 and 1. And if I think about just the function 1 over x squared, if we remember back to our p-series day, this p is greater than, not greater than or equal to, this p is greater than 1, and so this series or this integral converges. And so I can use that information to help inform my decisions, and since cosine is bounded by 1, I know that the integral from 2 to infinity of 1 over x dx has to be greater than the integral of 1 over cosine dx. And we can actually prove this using our improper integrals. So if we take from 2 to infinity, 1 over x squared dx, we can break that up. The limit as b approaches infinity from 2 to b, 1 over x squared dx. This turns into the limit as b approaches infinity, negative 1 over x from 2 to from 2 to b. And the limit as b approaches infinity, fundamental theorem of calculus, 1 over b minus negative 1 over 2. And the limit as b approaches infinity, this turns out to be 0, so this is 1/2. So we didn't have to go through all that. That was maybe extra practice if you needed it. But we know that since the integral from 2 to infinity, 1 over x squared dx converges, and that cosine squared x over x squared has to always be less than x squared, then our integral from 2 to infinity of cosine squared x over x squared dx converges as well. So when you are writing out the explanation to this one, you need to make sure that you write out, let me get up here. You need to give me that the integrals, one is greater than the other. If you can provide me that as a p-series, or we have already proved that it converges, then you may do that. Otherwise, you need to show that your comparison integral converges to a number, and then you need to tell me that since your new integral converges and your old one is less than your new one, then your original converges. So this is kind of wrapping it up for improper integrals. Please come to class with any questions. Again, this is really difficult, but at the same time, we've covered stuff like this with the improper integrals with bounds between infinity and negative infinity. So make sure to like and subscribe. And again, please come to class with any questions that you have.